Um, how's everybody doing? Check. Anybody? I am assuming most of you went to watch the eclipse yesterday. All locally? No? Did you go to South Carolina or somewhere?
My parents live in Western North Carolina. It was cloudy though, unfortunately.
Oh, too bad. Yeah, we went to South Carolina, Greenville area. We lucked out. There was no clouds, so it was really good. Um, so in the last class, we were talking about some examples to motivate why um, it's important and interesting to study airfoil aerodynamics. And these are all, like I said, examples from my own experience, just to help illustrate the different kinds of applications and how airfoils have to be tailored accordingly. Right? So we talked about low speed airplanes and high altitude airplanes where Reynolds number is low, and so these airfoils, as we are going to see later in the course, will have laminar separation bubbles, and a big task is to figure out how to manage these laminar separation bubbles. So we'll talk about all this in detail about what laminar separation bubble is and so on. But when you have to design airfoils for aircraft like this that fly at very high altitudes, this one went almost to 100,000 feet, then these are the sort of problems you have to handle. And then this is an airfoil, this is an example where I got a chance to design an airfoil for a general aviation aircraft. And here laminar separation bubble is not really a big problem. It is much more a problem of trying to keep as much laminar flow as possible to reduce cruise drag. So like I was saying, this aircraft earlier, it was originally designed with this RAF 48 airfoil, which is a pretty old airfoil. And when I was in Illinois doing my PhD, I got a chance to design an airfoil for this called the AS 5045. I won't go into details, but basically the idea is that if you look here, the new airfoil is this drag polar. So this is drag and this is lift in coefficient form. So in the cruise region, the new airfoil produces less drag, but then some people call it a waterbed theory. So if you push it in one place, it will come out in the other place. It's just like life is full of compromises kind of thing. So at high CL, this airfoil has more drag than the original one. Right? So you can say, well, what is the big deal? You got something here, but you lost something there. But it turns out that in these regions, the aircraft induced drag itself is pretty high. So airfoil drag doesn't matter too much. So you can actually compromise on airfoil drag. But here, airfoil drag is a big part of the total drag picture. So if you reduce something in this portion, it actually helps. And this will depend on each situation. So one of the things I did was to not just design the airfoil, but as I was designing airfoils, I was running it through an aircraft performance program to compare and see what the effect is on the aircraft performance. So these plots are rate of climb, and this color is the new airfoil and the blue is the old airfoil. And you can see that the top speed, so this is velocity, rate of climb, and when rate of climb becomes 0, that's your top speed. So the top speed was projected to go up by something like 10-15 miles per hour. But there is a small reduction in climb, like here, but that is pretty insignificant because in these regions, induced drag is a big player, right? So sometimes when you're doing an airfoil for an application, you don't get the full picture by just looking at the airfoil performance. You have to run it through the full application. You have to run it through the device performance calculation, and then you realize what's happening. So this is true not only for aircraft, but even for other applications like wind turbines or sailboats or something. Sometimes you really know what is important in the airfoil design problem only by going through sort of simulation of the full device. So this airfoil got used in a few airplanes, and this is one example. And like I was saying, my PhD was funded by Ford Motorsports for race car wing design. We'll talk a little bit about that in the course, but basically maybe many of you are very familiar with this, but downforce is such a key thing in race car aerodynamics, right? So that's because in a straight track it doesn't matter, but once the race car has to go around a curve, it's all friction is what keeps it on the track, and the faster you go, the more friction you need, and more friction means more downforce. Downforce always helps. So many of these race cars, produce something like 3 plus times the weight of the car in downforce. So they keep saying that you can actually drive a race car upside down on a track, on an upside down track, and it will still be stuck to the track just as long as you don't slow down. And they also say like they weld the manhole covers on these race tracks. I don't know if they're probably flush, but otherwise the race car going over it will actually pull up the manhole cover and cause problems. So one of the problems with these kind of wings is these wings are very low aspect ratio. So the 3D effects are really significant. So here is a picture that a colleague of mine in Illinois did. He did a CFD study, and you can see how the wake rolls up. And if you have taken wing theory or even aerodynamics courses, you know that the smaller the span, if it's a heavily loaded wing and small span, the vortices are really strong. So and many of these airfoils also have constraints from the rules. So what I've done here is I've plotted this airfoil upside down. So in the race car wing it will be the other way around, but for aeronautical engineers it's, at least I find it a lot easier to think about airfoils like this producing upward lift, right? But you understand it's in the race car it will be upside down. So the wings we were designing at that time had a box constraint like this, which means the geometry has to fit within a box, and they give you the dimensions, and just before the race they actually go and check many of these wings to make sure it fits the rules. So this box is imaginary, but they can put a device to check to make sure the rules are met. So if the race car is going along a horizontal track, V infinity free stream will come like this, right? The thing is, because of the downwash, there is going to be so much downwash that the actual free stream effective velocity vector that the wing sees is something like this. So you almost have to not design for airflow coming this way, but coming this way. And this itself will depend on the lift. So it was like a coupled problem. And so here's one example where the other, it's not just airfoil design, but at what condition you design the airfoil depends on other influences. Like here it was a short, stubby, heavily loaded wing, and sometimes there are all these things. So if you're designing the rear wing, you have the influence of all these front, the car body itself and the wheels. Those are all going to induce flow on the airfoil. So it's a really challenging problem. It's almost like it's a never-ending design problem, because just when you kind of figure out how to optimize this, that season will be more or less over and they'll change the rules. Then it starts all over again. So I'll post the paper that we wrote on how to design, how we came up with the design methodology, and here is the velocity distribution. So very soon we'll be talking about velocity distributions like this, and we'll talk about how to interpret them. But essentially, this is the area under the curve is the lift. So it ended up that because you have this box constraint, you can't design a very highly cambered airfoil for this application. The better way to design an airfoil is something like this. Even though it doesn't look like a very high lift airfoil, it has to work inside the rules, right? So that was the problem. So if you didn't have these rules, something like this would be really good. So some of our work resulted in the airfoils being used on some race cars, and that was nice. And since I came here, we have, with on and off with some students, we've been doing some race car applications, and Noah McKay, quite a while back, maybe 10 years more back, he looked at some wing design stuff for the SAE Motorsports team here, and then another student, Sriram Pakam, also was looking at airfoil designs for the motorsports car, and he came up with a design like this that has a very flat lift coefficient near stall, and that's actually pretty impressive, because many airfoils, the stall is sharp. Even these are pretty soft, but sometimes the stall is very abrupt. So you can keep on pushing angle of attack and then suddenly it will drop. But he tailored some of the way the separation moves to create a flat, like high CLmax region. And he tested it in the wind tunnel. This is our subsonic wind tunnel. And this is a comparison between wind tunnel and X-foil. And then, like I said before, I had a chance to work at Scale Composites, which is a company that's famous for designing lots of innovative and very pushing the envelope kind of airplanes. So these are some airplanes at scale. I was not involved with these things, but these are just some airplanes that were designed at scale. When I went to work I was just there for 2.5 months or something. I did airfoils for a new version of the Boomerang. So this was already flying by the time I went there, but they were developing a new version. And then after I came to NC State in 2003, I got a chance to work for the sailboat keels. So the America's Cup team from the US, Oracle BMW, I think this team is still going really strong. They won the America's Cup last time, I believe. Anyway, so the keel below the boat is actually essentially a wing, and it's a symmetric wing, but it's got tabs, or they call it tab. It's essentially a flap, and there are a lot of design considerations for these things. This was one more fun problem to work on. But most recently, you've probably been hearing of very light jets, and one example is the Cirrus jet, which has actually just recently been certified by the FAA, so it's going to go, it's probably in production already. So in 2005-06 time frame, I worked with the Cirrus engineers to design the wing and the airfoils. So the airfoils for this are NLF airfoils, natural laminar flow, and that's one of the things we'll be talking about in the course, why it's important and how to design them. And a lot of the concepts I used here are actually from the airfoil theory course and the other course I teach, wing theory. Just to sort of wrap up, I probably spent too much time on this, but it's not so. There are so many airfoils available in databases and catalogs, right? Many times, if you want to tailor an aircraft for an application, it's just best to custom design the airfoil. because every application has its own unique requirements. Sometimes something right off the catalog will work pretty well, but not always. So this course is basically tailored towards helping us understand airfoil aerodynamics and design techniques so that you will be able to look at outputs from say Xfoil and other codes and start saying, okay, this is what is happening with the airfoil. If I want to improve it for the low CL range, this is what I should do, and that kind of stuff. So that's what this course is about. Okay, so just as a sort of exercise to help us think about this, where's my teaching folder? Yeah. Okay. I'm going to show 3 applications, basically stuff I've talked about, right? Race car wing, rear wing. So rear wing is this wing, general aviation airplane, radio control sailplanes, and AeroVironment Centurion. And I'm going to show 4 airfoils, and I think I should download this so I can show it as okay, let's do it like this. So there are 4 airfoils. A, B, C, and D. You can't see the details, but I think that's good enough. Some of this is going to be obvious. So just in your notebook, match the airfoil to the application. We'll just take 2 minutes. It's a very quick, almost, yeah, like I said, one answer is immediately obvious at least. Okay, so those of you who are watching this offline, also, just take your notebook and make as good a guess as you can about which airfoil matches with which application. Okay, can we nail one application down right away? Yeah, of course. D is the race car wing, obviously, because I just talked about this, right? There's the constraint box, and this is just when we were designing it for that particular racing application. Every racing application has got a different constraint. Anyway, so this is a 2-element airfoil. It's got to generate high lift, but upside down. So high downforce. Here I've plotted it as in the aeronautical way. So it's going to generate high lift, but while having the constraint on the geometry. So you cannot tilt this airfoil and make it go outside the box. Okay, maybe now it's getting a little more challenging to identify which goes where. Um, okay, let's keep it like this. Okay, anybody else want to take a guess at which application will go for the other three? Any of the other three? Yeah.
I was thinking C might be the AeroVironment plane.
Okay.
Just because it's got a really high coefficient of lift where your drag is low. If that's what that plot is.
This one?
Yes.
This is actually velocity distribution. We'll be talking about it today. Okay? Yes.
Would A be the air environment?
Okay, why do you say that?
It looks like a negative pressure, or it looks like a reflex.
Reflexed. And why should that go to the AeroVironment?
For flying wing, for the he's a positive moment.
Okay, any other connections? Come on, somebody make a guess. It's okay if you're wrong. We're just throwing some things out. Yeah.
I guess the B one is the AeroVironment Centurion profile. I think it is that like a high lift airfoil because it's got a cast at the end.
Yeah.
So
It's not a high lift. Okay. I'm trying not to indicate what the answer is, just to generate some answers from you folks. It's interesting, all the three answers were for the AeroVironment Centurion. So I guess there's somebody who thinks each of this goes to the AeroVironment Centurion. What about the others?
Okay, so I think C is the radio controlled sailplanes, B is the general aviation airplane, and A is the aero environmental, because of the same thing for A, it's a flying wing
Yeah.
configuration. B looks kind of like the one that you showed us already for the general aviation airplane, and I'm not really sure why it's slow. I guess the sailplanes and the aero environmental airfoils should look fairly similar, because they're going to basically be gliders. They're going to be highly efficient, and they're not going to go very quick. And then B might be more structurally sound or something like a general aviation construction.
Okay, yeah, you're actually correct. So let's start connecting them. So obviously D is the race car. We can eliminate that. These two, right? These two are very typical of, we're going to see this. These two are typical of low Reynolds number airfoils. It's not even, maybe not even correct to say low speed, but low Reynolds numbers. That means Reynolds numbers of the order of 300,000. That's actually low, because if you go to a general aviation airplane, this is something like maybe 3 million, and the transport airplanes will be 10 million to 20 million or more. So this is 300,000 or 0.3 million. So you can see, for example, this is velocity distribution. We'll talk a lot about this, but you can see these two both have adverse pressure gradient from the beginning, even in cruise condition. So you can see this starts coming down, right? It's okay if you don't understand what I'm saying, because very soon you will. It's just a matter of few lectures and we'll be talking about all this stuff. But what distinguishes this, as some of you pointed out, is that this airfoil has got a reflex, and the AeroVironment Centurion is a flying wing, right? Or a tailless airplane. So this, because it doesn't have a tail, the airfoil has to provide trim or balance. The tail usually provides balance in most airplanes. That's not there. The airfoil has to provide that, and it has to provide stability. So you put the CG forward of the 25% chord, and you reflex the airfoil trailing edge so that it generates positive pitching moment. Right, so you can see the airfoil is tilted up here in the trailing edge. So I think about 4 or 5 lectures down the line, we'll talk about why this has to be done. And so the rear part of the airfoil actually generates negative lift. And when we look at what these plots mean, that will become clear that it's actually negative lift there. And because of the way the adverse pressure gradient is built in, these are actually for radio control sailplanes. So these sailplanes have airfoils like this. This is the series of airfoils I designed with my PhD advisor back when I was in grad school. So this is a series of airfoils with successively higher camber. And the last one is this. So this is the airfoil for the NLF airfoil, natural laminar flow airfoil for the general aviation airplane or the home built airplane. And here the pressure distribution is tailored so that in the cruise condition, so these two are the cruise condition. So you always have increasing velocity up to something like 50% or 70% depending on the application. So that supports a lot of laminar flow, and then you make it turbulent flow here. Laminar flow is less skin friction drag, which is really what you want for cruise. Okay, so hopefully, by somewhere near the middle of the semester, all this will actually make sense, because we would have gone into all the details about how to read these plots, right? Even to interpret this plot takes some thinking and understanding why certain things are happening. Okay, any questions so far? Okay, we are going to jump in and start the actual lecture material. Okay. So stop me if you have questions. So just to give a quick outline for the next few lectures. As much as possible, I'll give page numbers like this. So 2-1 means lecture 2, page 1. So we'll try to keep track of things that way. And I should remember to put autofocus off. Okay. So we're going to talk about some general definitions. About the airfoil, basically geometry and stuff like that. And then we'll talk about velocity and pressure distributions. So in some of these examples, we looked at velocity distributions, and we tried to say this is what the velocity distribution will do. It will support laminar flow, or it will create negative lift at the trailing edge and that sort of stuff. So velocity and pressure distributions are super important when it comes to airfoils. They tell a story about what the airfoil is doing. So what are these two? There are two of them, right? So we'll talk about connections between velocity and CP. CP is pressure, coefficient of pressure distribution. They are both interrelated. So what do these distributions tell us about lift, drag and pitching moment? And how do these things, these distributions change with angle of attack? And airfoil geometry like camber. And then we'll talk about favorable and adverse pressure gradients. We'll talk about a couple of concepts related to airfoil aerodynamics that people always get mixed up with. So there's something called center of pressure, or it's pretty much the same as center of lift, and aerodynamic center. And then we'll go into pitching moments, and tailless airplanes. Okay, so this is the general outline for a few lectures. Let's start with the general definitions. So the way this is going to work is Engineering Online will scan these pages and make it available. But there is a tendency, especially as the semester goes on and everybody gets really busy, and if some of you are watching this on video lectures, there is a tendency to watch the lecture at 2 times or 4 times the speed to try and speed things up and move on with life. And my own grad students have done that. They've come to me later and said, oh, you know what, I got all backed up and I watched 4 lectures in one day at 2 times the speed, and then I went to do the quiz and I couldn't do anything. So they went and this person went and watched these lectures again at normal speed. So just to make sure, and you really need to watch it at normal speed. Otherwise you think you're absorbing it, but everything is probably just not even entering your head. So I'm going to deliberately take away some pages from the lecture notes that are scanned. Okay, so maybe if there are 20 pages in a given lecture, maybe 2 will be missing on purpose. And the point is that you've got to pay attention, right? And if you're going to listen to me talking for 1 hour and 15 minutes, chances are you'll fall asleep. I mean, I will fall asleep if I'm not talking. So just to give you some activity, those of you who are coming to class, you're going to be fine because you're listening to me at normal speed and you're writing things down, and hopefully I'll put some activity saying, hey, do this little derivation or something like that. But for the video, those who are watching on video, so those few pages that are going to be missing, it's up to you to take a sheet of paper and kind of recreate what I'm doing in the video, just some activity. Okay, general definitions and terminology. So a typical airfoil is going to look like this. And we'll have something called, so the sharp edge is probably the easiest place to start from if you want to talk about geometry. That is the trailing edge. And since we'll be talking about all this a lot, we'll abbreviate it to TE. And the rounded edge is the leading edge. And that's usually this point. And if you draw a line connecting the leading edge and trailing edge, that's the chord line. And this surface is the upper surface, and we'll be talking about it like aeronautical engineers, not like a race car engineer, right? So for race car people, that will become the lower surface because they put it upside down. And this is the lower surface. Again, the abbreviations we're going to use are US and LS. Okay, so usually the trailing edge is very well defined and the leading edge is not. How do you choose which point along this rounded edge is the leading edge? So and what I mean by that is, let's say you have some airplane available to you that you're sort of reverse engineering and you want to figure out what airfoil that airplane is using. Right, so you can take the wing and put it on some kind of coordinate measuring machine or some geometry scanning machine and it gives you coordinates like this. Right, it will give you the trailing edge and then it will give you all these points. And this is like maybe a lot more points, right? I'm just drawing some few points for illustration. It's not going to give you the geometry with chord line level, right? It's just going to give you how the airfoil section is situated at that particular instant. So how do you go about deciding which is the leading edge? Trailing edge is usually easy. That's this sharp pointy place. What is the leading edge? Any quick thoughts? Some of you who have done aerospace engineering, I think you've had to decide this or we have talked about it, right? How do you know which of these points or where along this curve you should put the leading edge? Yeah, right, that's all it is. So the longest distance from here to anywhere along the airfoil is the leading edge. So if obviously this is not it, then you can go here, you can go here, and then you probably come to some point here that will be the longest distance, and then after that the distance will start reducing. Right, so this is the leading edge. So this distance is called the chord, and normally we so this is the chord. So normally we draw the chord horizontal just for convenience purposes. So we take this geometry and we rotate it to something like this, and this is the chord. This distance is called the chord length. And that's usually denoted by symbol C. So chord and chord length are somewhat interchangeable. Somebody really you should say what is the chord length of this airfoil, but they'll just say what is the chord of this airfoil. It means the same thing. So chord connects trailing edge with the leading edge, and it's the longest distance on the airfoil for any segment connecting trailing edge and any other point on the airfoil. Now in an actual application, which end is the front end and which is the back? Which way will the flow come? Right, towards the leading edge, right? So flow comes this way. So the flow, that's why it's called the leading edge, because the aircraft, the leading edge goes in front obviously, and this trails behind. Are there situations when this is not the case? when maybe the airfoil is actually going like this. So the airfoil goes like this, or flow comes this way. Yes, tell me. What is it? Yeah, wind turbine. Okay, yeah, there are situations. You were nodding your head, right?
Also helicopters.
Sure, helicopters. Many rotating devices. You don't want this, but it will happen. You have to live with it, kind of thing. So there are instances in rotating devices where the flow will end up coming from trailing edge to leading edge. And an example is, it can happen in wind turbines, but the example I'm going to give is for a helicopter rotor blade. So just as an aside, so a helicopter rotor blade is, I'm going to show the plan form. So here's the blade, and so this is, let's say this is a helicopter in hover, and the blade is spinning like this, and so the circle is going to be kind of like this. So the helicopter is in hovering mode. It's not moving forward or back. It's just in one place, right? So because the rotor is spinning so fast, the tangential velocity experienced by the airfoil is going to be like this by the different sections on the blade. Right, so this section will see a certain airflow because of rotation. The airflow is completely due to rotation. This section at the tip will experience much greater airflow, and when it's on this side, it will experience airflow from here, right? So that makes sense. Now, when you put this helicopter in forward motion, some interesting things happen. It's kind of obvious, but the first time you learn about this, it's like, wow, I didn't even think about it. So this helicopter blade is rotating. Right, so it's rotating like this, and the helicopter is moving in this direction. So if you want to think about it, this is V infinity, this is the free stream, this is the relative velocity of the air due to the motion of the helicopter moving forward. So this is forward motion. Well, strictly speaking, this is forward motion. This is what we call free stream. We'll talk more about it if you're not too familiar with it. So what we have to do now is, there is going to be, every blade section has got velocity, tangential velocity due to the rotation, which is the same as this, assuming it's the same RPM. On top of that, this free stream is superimposed. So what happens is, you get a velocity variation like this. So this tip, this is called the advancing blade. And this is called the retreating blade. So this tip will get a much higher velocity, tangential velocity of the air coming towards it, because you add the rotational velocity contribution and the free stream, and that's what you get here. You actually do this everywhere. So there are portions in the um, middle of the retreating blade in the hub region which will actually have reverse flow now, because you're adding tangential velocity of the air due to rotation coming this way and then free stream coming this way. And so in the region where the free stream is higher than the tangential velocity, and it will actually be a circle, this region has got reverse flow. So, in all these forward flow places, the relative airflow is actually going to come from this direction. This is forward flow. And then in the reverse flow region, the airflow is actually going to come from trailing edge towards leading edge. But there's really nothing you can do about it. That's the way it is. So helicopter flows are very complicated. This is one of the reasons why they are very complicated, is because these airfoils end up working in reverse flow for a certain portion, and the faster the helicopter goes, the bigger this reverse flow is going to become, right? To the point that when the helicopter is going really, really fast, this reverse flow can become a big enough circle that it comes all the way to the tip, and that is so far, no, I don't think any helicopters have flown in that regime. So one of the reasons helicopter forward speed is limited to a certain extent is they can't fly as fast as airplanes, not yet anyway. This is one of the reasons. There is another thing called dynamic stall that occurs, and that's another limiting factor. And so because people are interested in making helicopters go fast, they have this really big advantage that they can take off and land vertically. So airplanes can't beat them at that. But then airplanes are much faster. So of course helicopter people want to, they are challenged by the fact that they can't go faster. So they are coming up with all kinds of ways to make helicopters go faster, and to do that, one of the things they have to figure out is how to simulate reverse flow and how to design airfoils so that they function in both forward flow and reverse flow. That's the thing, right? This airfoil is not always in reverse flow. As this is spinning around, here it's in forward flow, here it's in reverse flow. So if you think of an air being still and an airfoil moving, it's like this airfoil is doing this. So how do you, first of all, how do you figure out what that's doing? And then second is how to go and improve it or design it better. So actually one of my master's students is trying to, her master's thesis is about simulating airfoils in reverse flow with a low order method, not with CFD. CFD can do these things to some extent, but how to do it in a very quick, easy way for design purposes. And she's actually defending this Friday. So we have a lot of interest in that topic. Okay. Now I was saying how the trailing edge is very straightforward to define because it's the pointy edge, but even trailing edges can have different shapes. So let's talk about different trailing edge shapes. So the one difference is a sharp trailing edge versus a blunt trailing edge. So this is a sharp trailing edge, and a blunt trailing edge is obviously one that's like this. And there can be many variations. You might have a rounded trailing edge for some reason. For example, some of those helicopter sections where they encounter reverse flow, the trailing edge is rounded. some of them have almost like elliptical looking airfoils because these airfoils have to work well in forward flow and reverse flow. So there's no such thing as this is front and back, right? It keeps switching. So those are all there, but generally this is a sharp trailing edge and this is a blunt trailing edge. And so the question becomes, what do you call the trailing edge now, because this is not a single point. Usually this point is you take this as the trailing edge point. And in reality, most airfoils are going to be blunt trailing edges like this, because from construction viewpoint, you cannot make a perfectly sharp trailing edge, and plus from practical reasons that's not necessarily good, because if somebody goes and bonks their head on this, it's not safe. So they make it blunt. It's also easier to fabricate. And in some ways these are actually a little bit better aerodynamically. But a lot of the analysis we'll be doing is for sharp trailing edge. You can do blunt trailing edge, but it's not a very different, completely different thing to have a slight bluntness. Okay, so we will probably talk about sharp trailing edge much more, but when you end up fabricating it, it will become a little blunt. So another trailing edge shape classification is, so this is within the sharp trailing edge. So you can take the sharp trailing edge, and there are two types of sharp trailing edges. One is called a cusped trailing edge, and the other is called a finite angle . So a cusped trailing edge is one where the upper and lower surface meet at the trailing edge tangential to each other. Oh, sorry, yeah. So this trailing edge angle is 0. So here upper and lower surfaces meet whereas a finite angle trailing edge is one where they don't meet tangentially, they meet at some angle. So later, a little later, we'll talk about the velocity differences between these two. Okay, so one of the very first things you do in aeronautics is, or one of the very common things you always talk about in aeronautics is angle of attack, which is denoted by symbol alpha. Right, let's talk about the definition. Because there are situations where the definition of angle of attack changes, even within airfoil aerodynamics, and definitely when you go to aircraft, there are different possible definitions. Somebody could take an aircraft and draw a line through the fuselage and say that's going to be used for angle of attack definition. Somebody could say take the wing root and say I'll take the chord of the wing root and use that. Then the wing tip is different. So it's just like all kinds of definitions depending on the situation. So we are going to use this more or less uniformly in our course, but be ready to be flexible because later on in some situation you might have to use something else as an angle of attack, and you just have to be aware and paying attention. As long as you do that, it's straightforward. So let's take an airfoil like this. This is the chord line, and the chord line is usually put along the x-axis, and let's say the free stream velocity is like this, v infinity. Then this angle is alpha. So this is the free stream velocity vector. And we'll usually denote it by v infinity with an vector sign when you're talking about the vector property. And the thing to remember here is this is the velocity of the flow far upstream. So for convenience purposes, we usually draw this arrow near the airfoil so that you can denote the angle and so on. And after many years of doing that, you slowly forget that this is actually indicating the direction of the flow well upstream. Because if this is the flow far upstream, when it comes close by, the flow will tilt. The airfoil itself will make the flow tilt. That's not what this is showing. Even though you might draw it here, sometimes you draw it really close like this, right? Just for the purposes of definition and indication and so on, you might actually draw a free stream like this. That this is really not the flow here, it's actually the flow far away here. Here the flow, if you put this flow far away, here the flow might actually be like this, right? So just remember that even though we draw this here, this is actually the far upstream flow. So alpha is the angle of attack, and that is the angle between v infinity and the chord line. And it's positive as shown here. And so because we sometimes forget that this is free stream velocity vector, people, even when they want to figure out what the angle of attack is in an application. So one of the really messy things with aerodynamics is you can't, measuring angle of attack is a tricky thing. So people have tried many things. So on an aircraft, for example, you might put a sensor like a angle of attack and yaw right. So if you want to measure the angle of attack, one way to do it is to put a boom so that hopefully you go a little upstream of the fuselage, because the fuselage itself will influence the flow. Ideally you want to know what is the flow angle far away relative to the body. So you can put a boom and then you can put an instrument called the yaw, angle of attack vane and the yaw vane. So if I zoom into this will probably be a boom like this, and here's the fuselage, let's say, and this boom will have essentially something like a weather vane, right? So this weather vane is able to tilt, and that it will tilt and line up with the local flow, and that will tell you, if you have a potentiometer that tells you the angle, it will tell you that's the angle of attack. These are all, messy things, because first of all, anytime you put a boom and try to put this thing far away, this boom is going to start vibrating, and it's going to have its own kind of structural deflections, and that's going to cause problems. If you don't put it far away, and if you put it close, then the local fuselage or wing, you can put this on a wing too, you can put this here. The wing itself is affecting the flow, so what you're measuring is not correct angle of attack. So then people will come and correct it, right? So they'll say, well, let's live with a short boom, but then we'll use some calculations to say if the measured angle of attack is 5 degrees, it's actually 4, because you do some calculations and say this is the correction factor you have to apply. And then there's question about, is this correction factor correct? So all these problems happen. So some people, like in a race car wing, there was somebody who actually suggested something like this. So race car wings have end plates. So let's say this is a race car wing and this is an end plate. Let's see, show you what I'm talking about. So you can see here there are end plates, right? These are the sort of plates that cap the wing on both sides, and they help to reduce the trailing vortex effects, and so they're always used. So somebody was saying, well, maybe we can do oil flow whiz on this and see how the streak lines are, and that angle will give the angle of attack. Now we just saw that that's not correct, right? So that's the flow near the airfoil, so you can't say that's the angle of attack. So this is one example of how we sometimes, after using this for a long time, we forget that this angle, this vector is really denoting far away, far upstream flow. So anyway, so this is one of the practical problems in aerodynamics, is to measure angle of attack. Another student of mine, Maria, she's defending on Monday. So with she's doing the other topic. No, my PhD student Aditya Saini, he's actually come up with a way to have 5 pressure taps. He's just finished his PhD, and with these 5 pressure taps, we have tried to. It's working actually pretty well, as long as until stall. So by knowing these 5 pressure taps, we have come up with an algorithm to say this is the angle of attack for the airfoil. So this is one kind of persistent problem in aerodynamics. Just so that you know that people have been trying to solve this for many years. Okay, so now let's talk about what happens if you have a flap on the airfoil. So most practical applications will have some kind of flap usually. It can be a control surface like elevator, rudder, aileron on an airplane. Those are all, but essentially for the airfoil section it's like a flap. So here is the basic airfoil, and the trailing edge portion, something like 20% of the trailing edge, the last 20% of the airfoil is usually a movable surface so that you can move it up and down, and that's called a plane flap. So the airfoil will be cut out like this, and then this flap will rotate so that it can deflect like this. So that's what gives you can use it to control the lift on this surface. So that's what ailerons and rudders and elevators do. Or you can use it to increase lift for the purposes of landing. So there are many kinds of flaps. What I've drawn here is called a plane flap. Now, I actually drew this too big, so maybe let's fudge this. So this is the chord line for the basic airfoil, right? The airfoil without the flap angle changed. Flap angle is 0. So usually the way you define flap angle is, this is called flap angle. And it's denoted by symbol delta F. And if this is an elevator, it will become delta E, and so on. E for elevator, R for rudder, A for aileron. But here we are just talking about it like a flap. And usually this is positive as shown here, positive deflection. And this is called a plane flap. And this is the trailing edge of the undeflected airfoil, and this is the leading edge. And let's say the free stream velocity vector is this, and this is angle of attack. So now the question is, when you deflect the flap, the trailing edge becomes this, right? So now how do you define chord? Is the chord the line joining this trailing edge to here or this trailing edge to here? Geometrically, this trailing edge is not there, it's moved here when you deflect the flap. So go ahead.
The lower one.
The lower one, okay. Other thoughts? Anybody don't agree? So in practice, actually, you always keep this. This is the chord line, and this is the angle of attack, even though the flap moves here. So you set the flap at 0, and wherever the trailing edge is and leading edge is, you connect that line. Even though after you move the flap, that line is like an imaginary line, right? Yes?
So I have a question. This is just from some of the stuff we worked with flaps that kind of extend instead of they're slotted. So you actually end up with a longer airflow shape. Would you still, we took the longest value part so that when you were not dimensionalizing it, you weren't ever going above 1. So would you go with that? Is that you were still going to use when it's like closed?
So the question is, when you have a slotted flap, is that what you had?
Well, we had a three-part airflow. So we had a slot and then a flap. And when it was in full landing position, it was longer.
So there are airfoils where the flap will actually nest. So this is how the airfoil will be, and then when you deflect the flap, this flap will not only deflect downward, it won't just pivot. It will pivot and come out, or the pivot might be outside. So for example, if the pivot point is here, so you could have a mechanism like a flange or something connecting this to the main airfoil, and then this flap will have another one, and there will be a pivot point here. It's a simple hinge. Sometimes it's not a simple hinge. Sometimes you'll have tracks on which this flap will slide out, and then it will deflect at higher angles. So big airliners, like most transport airplanes, will have, those are called Fowler flaps, where they come out, so they'll extend the chord and then they'll deflect. So for takeoff, it will just come out and it will maybe deflect 10 degrees, but for landing it will come out much more and it will deflect all the way to 60 or something like that. So this slotted flap is a simpler version of that. So when you deflect it to 45 degrees, for example, it will look like this. So the question is, I guess, how to define chord and angle of attack and all that, right?
Well, just for when you look at figures with that, like the coefficient of lift or the pressure distribution under it, suddenly if you normally non-dimensionalize against the chord length, your chord
Yeah.
length is changing.
Yeah. So usually the chord is defined as what is for the original airfoil. So even though you might have a pressure distribution on the deflected airfoil that looks like this. This is the main airfoil, and then the flap is, let's say, like this, and so this flap deflection will be, flap pressure distribution will be something like this, right? I'm just sketching something. But the actual chord is this. You can do anything you want, and as long as you stick to that, you'll be fine, right? So suppose you declare that in all my calculations, I'm going to use this as the chord, and if you know what it is and you non-dimensionalize to that and carry that consistently to all calculations all the way to the airplane calculations, strictly speaking, there will be no problem. But usually in data books and other things, you stick with this as the chord. This is the chord length, and this is the chord, actual chord line. And you say, I'm going to use that as the chord for everything, undeflected, completely deflected. And it's just a reference quantity, right? It's just how you're dividing. The good thing about this is you're always comparing improvements in lift due to this to the original geometry. So you take this as the original geometry and CL max is 1.1. When you go to the deflected geometry and say CL max is 2.1 with this as the definition, then the increase in lift is proportional. It's 2.1 over 1.1. But if you keep changing the chord for each angle, if it's different, then you can't anymore compare CLs. So that's the reason usually this is how it's defined. There may be reasons when you don't do this, like in a race car wing, it's always something like this, right? There is no sort of nested configuration where it's a simple airfoil and then it comes out. It's always some complicated two-element shape. Then you define something as the reference length and stick to it and say that's what I'm going to use for my reference length, and I'm going to call this the reference length. So for example, in this, when we were doing this work, we decided that it's not the chord, but this is the reference length we use for all calculations. Whether the airfoil is like this or whether I change this flap and move it here, right? If I make the flap like this, if I use this as the reference length for all calculations, then I can compare all of these airfoils and just use this lift coefficient and say if lift coefficient increases, that means more lift. Does it make sense? Okay, so we'll talk some more about this, but this length is the chord length. Usually that's what is used as the reference chord. Okay, so this original chord length is what is used as the chord C, even for the deflected case. And that is the line that's used for angle of attack definition. So usually, and I'm saying usually because in some cases they may deviate from this rule. So one of the things you have to be careful about is figuring out what definition somebody has used. Some data book or something. Let's say you go and you're reading a report and they're giving all these data about this airfoil, then you should try to figure out, and hopefully they've documented it correctly, is what exactly is the chord, especially in situations like this. Usually there's no confusion. But if you have situations like this, the chord line and alpha are based on the original geometry. So just to be clear, chord line is kept the same for the zero flap case and the flapped case. I think we're out of time. Yeah, I thought I'd set up an alarm to kind of remind me what happened to it. Well, I'll stop here. We'll meet on Thursday.